Okay, we are going to go through the problem 5.083. This is the problem that we need to use the Thevenin equivalent of the network in the figure below to find at the terminals AB. So we want to find the VOC at here, and also want to find the R Thevenin. So in this problem, because we only have a voltage, we have a dependent source over here, we're going to apply a current source. And we're going to apply the current 1 milliampere current source. So I put a 1 milliampere current source over here and solve it, and I'm going to take out this 1 milliampere. I'll cover this 1 milliampere current source at the end. So this is just to solve it, because without having a current going through it, we cannot find the Vx, and if we don't know the Vx, we don't know the current that is coming here. So basically we have to add something and just take it out at the end. So in order to solve this problem, I'm going to do a KCL at these two nodes. So this is, I call it node 1, and this would be node 2. And if I want to find, if I want to write the KCL at node 1, KCL at node 1, I have to write, okay, v1 minus v1 minus 0 over 2k. So 1k plus 1k is 2k. So v1 over minus 0 over 1 plus 1k. Then I have v1 minus v2 over 2k plus v1 minus v2 over 2k. Then I have the vx over 1000. So I can say v1 over 1k, vx over 1k plus, so this would be minus, because this is coming to the node, I have to write it as minus vx over 1k equals 0. Okay, then I have to know what is the Vx, right? So Vx here is going to be, if I know the V1, so Vx, I have to do a voltage division to find Vx. So Vx is V1, so Vx is a voltage division. I have to do the voltage division. So Vx is V1 over 1 plus 1 times 1k. So this is 1 plus 1, and then how much is the voltage is dropping over here is going to be the Vx. So this is going to be 1 plus 1 is 2, so Vx is actually V1 over 2. So if I put this relationship over here on this one, so I can rewrite this as V1 over 2k plus V1 minus V2 over 2k minus, okay, Vx is V1 over 2, so this is V1 over 2k equals 0. So you say that this is V1 over 2k and this is V1 over 2k, so they cancel each other out. And then if this is equal 0, we conclude that V1 is equal V2. So I write the KCL at node 2, KCL at node 2. So this is the node 2, so I say V2 minus V1 over 2k, V2 minus V1 over 2k, and then I have V2 minus 0 over 1k plus V2 over 1k plus, and actually because this is coming to the node, I have to write it as minus 1 milliampere is 0. So knowing that V1 is equal to V2, so V2 minus V1 over 2k is going to be 0. So V2 over 1k is 1 milliampere. V2 over 1k is 1 milliampere. Then I conclude that V2 is 1 volts. So if V2 is 1 volts, then V1 is also 1 volts, because V1 is equal to V2. And then if I know the voltage over there, and then I can write the Vx over here. So Vx is also going to be half of the V2, so this is a half, so one Vx over 1k would become so like half a volt over 1k. So this is the other thing that we can write over here. But what is important for us here is to find the R-Thevenin. So how do we find the R-Thevenin? The R-Thevenin is going to be the voltage at this end that we can find. So like the V2, if I know the V2, and then I can write the R-Thevenin is equal to my voltage across it, across this, over the resistance of over the current that I'm having. I have actually put this test current over there. So I put it as the voltage 1 volts over 1 milliampere. Then my R-Thevenin is going to be 1 kilo ohm. So if I want to redraw this circuit, I have to redraw it like this. I have a 1 kilo ohm over here, and then I have this 1 milliampere over here. But because this is what I added to that, my whole circuit is going to be 1k. So because I promised that I'm going to take that one out at the end. So there is a 1k over here, and VAB is going to be VOC, V open circuit, and then VOC is going to be 0. Make sure that when you are adding that, you have to put it as VOC is equal to 0. And then this 1k is going to be actually the equivalent resistance, or it is the R-Thevenin.